Well, welcome back, or welcome if you come especially for this lecture. It's a particular pleasure to introduce the last speaker in Science Week, Professor Andy Carter, because Andy is one of the longest serving Birkbeck members of staff. He came as a school leaver before he got his degree, did his degrees here, worked up through the technical staff, transferred to being an academic staff, and is now one of our leading professors in Earth Sciences, which is a particularly Birkbeck story. It's a great pleasure to introduce Andy, who's going to talk about understanding how and when Antarctica became a frozen continent.
Thank you. Thank you, Nick. So I'm a Birkbeck fossil. Okay, so following on from the theme of the previous two talks, we'll be looking at Antarctica in the context of climate change. And so the message I want to get across to you this evening is that to understand modern climate change, we need to understand and explain the causes and consequences of past events. Now, Philip outlined some of his research trying to achieve that. What I want to do this evening is to show you how it's a challenging thing to try and understand past events using our existing climate models, for example. So if we think about the climate change and climate models, we have predictions coming out of the Intergovernmental Panel on Climate Change about future change. These predictions are largely based on climate models. The climate models are based on descriptions of the physics of natural processes. Now we know something about the individual processes. We're fairly confident about the physics. But what we probably don't have a full appreciation of is the causal connections between meteorological and environmental phenomena, the so-called teleconnections. So one of the things that we can try and understand better in terms of these teleconnections is to look back at past events. And Antarctica is a good illustration of that. So in this talk I'll say something about the hypotheses that have been put forward to explain why Antarctica became frozen over with large ice sheets. Look at the evidence for changes in global temperature associated with that. A bit more about carbon dioxide, expanding bits of that in relation to Antarctica. And look at some of the research I've been doing for evidence of early ice on Antarctica, and then ending with some of the latest research that sort of explores these teleconnections, because it has direct relevance to the climate models of today. So this is a slide that many people use when it comes to talking about Antarctica, in terms of getting across how much ice is stored. It holds 90% of the world's ice and 70% of its fresh water. So there's an enormous amount of water stored there that if that were to melt in a warming climate, it's going to clearly raise sea level. The question is by how much. So here's our measure. Here's Big Ben. Or the tower, Big Ben's in there, but the tower goes up to 96 metres. Where do you think, if we melt all the ice on Antarctica, where do you think the sea level is going to rise to? If I keep moving out slowly, you tell me when to stop, when you think it's reached the maximum amount of sea level rise. About there?
Yeah.
No.
Keep going or go back?
That deals with the MPs anyway.
Keep going? Well, that's the other thing, isn't it? More? Try there? Yeah. It's about there, 57 metres or so. So that's a significant sea level change. Of course, that's an oversimplification because it won't be quite that because of the water load. But nevertheless, the Thames Barrier is not going to help us. So, Philip was talking earlier about the warming climate. We're seeing evidence of the ice sheets breaking up, the large ice sheets over here are fragmenting. Sea level is going to rise in the future. Don't be a doom. Now, a complete change of tack. A couple of years ago, I was asked to give a talk to a local society on the geology of Essex. Any of you who know Essex know that's a bit of a challenge, because if you want to find any rock in Essex, there's only two places really: Thurrock down here near the Dartford Tunnel, where they've quarried all the chalk away, or somewhere up there in Saffron Walden. The rest of Essex is covered by sand, gravels, and a hell of a lot of clay. So it's pretty dull, you might think, in terms of geology. Not so, I would argue, being an Essex boy. The interesting bit is that the clay spans two important periods. We have the London clay, which is 50 million odd years old, associated with the Eocene era. And we have the very young Pleistocene clays associated with the last ice ages. So you can see where I'm going with this. In the Eocene, the London clay, it was a warm, tropical climate, rather like Indonesia today. The coastal areas were densely vegetated, and from the fossils that have been found so far in the London clay and associated sands, there are over 350 species of plant that have been identified. One of the world's most diverse fossil records of seeds and fruits. So it was a very lush, rich, warm time. By contrast, the Pleistocene younger clays are associated with the Anglian ice sheet that more or less reached London some 450 years, 1,000 years ago. And there was a succession of ice sheets right up to about 11,000 years ago. So we had a very cold climate. So Essex is recording two extremes in the Earth's climate. So Essex would have looked something like that 400,000 years ago. So here we are. This shows it rather nicely on this plot, which shows the so this baseline here is modern temperature today, and we're looking at departures from that in the past. So when the London clay was around, global temperatures were some sort of 16 degrees hotter than present. When we had the glacial tills deposited, we were 2 or 3 degrees below global average temperatures, which are around 14 to 15 degrees today. So two very different climate regimes. And we had this period of cooling between them, and at some point, most people believe around 34, 33 million years ago, we had this sudden expansion of ice across the whole of Antarctica. So one of the key questions then is to explain, what is going on with these long-term trends. Now we've heard something about the creation of the Himalayas and increased rock weathering, and I'll come back to that in a minute. In terms of why people have put forward suggestions that the ice sheets expanded at about this time, if you go to Antarctica, we can't look for evidence of early ice in these regions because it's covered by several kilometres of ice. The only areas where we can find past evidence of early ice is around the coastal areas or slightly offshore in the shallow marine areas. So a nice paper came out in Science at the end of last year from a borehole that was drilled into soft sediments in this region here on the edge of the Ross Sea. And for the first time, this showed that prior to 33 million years ago, there was periods of ice encroaching. You can recognise specific types of sand grains that record the presence of ice in the sediments, which I'll show you some examples later. So there's very characteristic sediments that you can say, yes, ice was around, ice is gone. So they were seeing at a single location, ice expanding, ice disappearing, ice expanding, ice disappearing, until 33 million years ago, then there was permanent ice. So they took that to be the time at which the ice sheets formed. And similar other studies around the region have found a similar sort of timing. So that's the evidence that people have for the early ice sheet. Now, why did Antarctica freeze over at that time? If we go back to this thing here, we had obviously cooling, but there must have been some sort of tipping point here reached for the ice to expand. Now, what caused that? There's two main hypotheses that have been put forward. Plate tectonics, and that really is arguing that as the continents broke up, the ocean circulation systems changed because you had new pathways for ocean currents. And that led to what is known as the thermal isolation of Antarctica. In other words, the warmer waters from the equatorial regions couldn't penetrate further south because they were cut off by these new ocean currents. So Antarctica was colder. And then there's the CO2 hypothesis, the greenhouse gas hypothesis, where we have this progressive decline in atmospheric CO2 concentrations, and again you reach a sort of critical point where the CO2 was so low, global temperatures are cooled enough that Antarctica froze over. These are sort of, in a sense, two end-member hypotheses. Historically, this was the first one to be put forward back in the sort of 1970s, 1980s. And more recently, this hypothesis has been pushed more and more in the advent of these rather complex climate models. Now, if we take a step back and say, well, why are the polar regions cold? They're cold because, if you think about solar radiation colliding with the Earth, because the sun keeps us warm, in the sort of equatorial regions, solar radiation is focused on a relatively small area. So that area warms up more than at the polar regions, lower latitudes, where the solar radiation is deflected over a larger area. So there's a very strong latitudinal control that we have in terms of warming from the sun. We always expect the polar regions to be cooler because they're receiving less solar radiation, or it's dispersed over a larger area. So, given that state of affairs, polar regions are cooler, but you're not going to develop ice until the surrounding oceans are cooler as well. If you've got warm ocean waters surrounding the continent, even at polar regions, it's not going to be frozen over. Now, if we look at reconstructions of past global sea surface temperatures, at the time of that big spike on that plot I showed you, what is known as the Paleocene, Eocene thermal maximum, that's 50 million years ago, sea surface temperatures were at around 0 degrees, the equator, around 40 degrees, compared with, 30 odd today. But more importantly, you can see at the lower, north and south poles, they were still quite warm relative today. How do we know this? What do we base our sea surface temperature estimates on? Well, people use oxygen isotopes that Philip mentioned earlier. So we get these reconstructions of oxygen isotopes. They look at the abundance of isotope, these stable isotopes of oxygen. Most of it is in the form of oxygen-16, and the ratio is going to be a function of temperature, or sea temperature, stroke global temperature, for the reasons that I'll show you here. But because of the different weights in these isotopes, if you're evaporating water, O16 is going to evaporate more easily than O18. So if you evaporate the water and you precipitate it out, if you store that water then as ice, doesn't get back into the oceans, you increase the oxygen 18 rate amount in seawater. So your oxygen isotopes ratios will change through time, more so if you've got ice. So if you have massive freezing over of Antarctica, the oxygen isotopes evolved. Now that basic principle, there's a lot more to it than that. That basic principle is what people have used to get these global compilations of temperature change through time. And it works because if you've got something living, a little bug, like a jellyfish, or a shell in the sea, the calcium carbonate tests will store the oxygen isotopes of the surrounding water at the time they're living. So people look at the fossil shells, extract the oxygen isotopes from those shells. If you know the age of those shells, you know the sea surface temperature conditions at that time. I'm oversimplifying, of course. So this guy, Zakos, back in 2001, I think there was an earlier paper than that, that's the main one. He produced the first global compilation of oxygen isotopes, which is a proxy for global temperature or sea surface temperature variations through time, covering the last 65 million years. So it's on this basis that we know the climate was a lot warmer in 50 million years ago, and it's a lot cooler today. So we know from proxy data, such as these oxygen isotopes, that the Earth was clearly warmer and got cooler. What drove this decline in temperatures? Is it as simple as CO2 being removed from the atmosphere by silicate weathering, for example? Once Zakos produced his curve, other people looked at other sources of information. They looked at reconstructions past sea level, and they noticed that sort of mirrored the trend in oxygen isotopes. They looked at other proxy data for deep sea temperatures using other elements, ratios. And there's proxy data for atmospheric CO2. There's a number of different ways you can get at that, including looking at the pore size and number of pores on fossil leaves, because that tells you something about the state of the atmosphere, stomata. And boron isotopes, which is perhaps the most preferred method these days. Anyway, if you look at the CO2 reconstructions, you look at the oxygen isotope reconstructions, you can see they track each other, don't you? So if you look at that, you might think, well, yeah, that's the cause. Our greenhouse gas effect is causing, driving that cooling. But is it that simple? So, as Philip has pointed out, CO2 is our greenhouse gas. So it follows that we have incoming solar radiation, it gets converted to infrared. Some of that infrared radiation is then reflected back into space. What stops it going into space is clouds, atmospheric CO2, and a few aerosols. It follows then that if we reduce the amount of CO2, more radiation is going to be reflected back into space, so the Earth will get colder. That's the very sort of simplistic way of looking at the CO2 cooling mechanism. So, what have we established so far? Global temperatures have fallen systematically since about 50 million years ago. The levels in the CO2 in the atmosphere have fallen systematically, with a few little blips along the way. Why? What drove these changes? So Philip was talking about this cycle of CO2 production from volcanism, that is to say, the release of CO2 from the molten inner Earth. If we had no humans, that would be the main source of CO2 to the atmosphere. And in the natural world, that CO2 is stored by organic matter that gets deposited in the oceans, and most of it is extracted by these rock weathering reactions that Philip outlined. Now, I've got a solution for the global warming crisis, and it's quite simple. We stop all the man without gassing, and we kill off mankind. Because if we do that, and we're not putting any CO2 into the atmosphere, these weathering rates, these silicate weathering reactions that Philip was talking about, they're extremely efficient. If we look at the rates of silicate weathering from all the rivers going into the ocean, so we can get a measure of how much CO2 is removed by that. We currently have about 720 gigatons, billion tons of CO2 in the atmosphere. Okay, it's a lot. It's equivalent to about 2,000 times the weight of the entire human population floating around in the atmosphere. With silicate weathering has a removal rate of about 0.6 gigatons a year. So if we were not putting any CO2 into the atmosphere and we killed all of mankind, then it would only take 1,300 years to remove all of the CO2 from the atmosphere. Of course, that's a gross oversimplification, but it gives you some idea about the efficiency of the silicate weathering as a natural process. So that's why when you see plots like this, we have annotations in terms of this cooling trend, Antarctic glaciation taking place here, formation of the Himalayan belt, hereabouts. Why is that on there? It's on there because the creation of these large mountain belts accelerate or promote increased rates of weathering and therefore increased rates of CO2 drawdown, and hence the global cooling trends that we're seeing there. The Himalayas, it must be said, is the largest mountain belt that we've seen created on Earth in the last 500 million years. It is massive in the grand scheme of things. So it's clearly going to have a profound influence on the weathering rates on Earth. So I'm not saying that formation of the Himalayan mountain belt isn't unimportant, it clearly is. But in terms of the freezing over of Antarctica, it's not just the CO2 story. So the common view about the large ice sheets forming on Antarctica, they nucleated about 34, 33 million years ago. What that means is there were glaciers, large glaciers present before that. But by the time you got to 33, 34 million years ago, these glaciers had expanded and you had large ice sheets covering virtually the whole of the continent. So people hold this view that there was a tipping point somewhere around 600 to 900 parts per million. Once CO2 went below that level, you had conditions favourable for the ice sheets to expand, to nucleate. But what about tectonics? We heard about plate tectonics earlier. Our hypothesis one, the original hypothesis for the freezing over of Antarctica, favoured a tectonic explanation. The tectonic explanation relates to the separation of Australia, Antarctica and South America, which were joined together some 100 million years ago. And they started to break up and split apart from about 70 million years ago. And when they separated, you had new pathways for ocean waters to move around the continents. So it caused a fundamental reorganisation of the ocean structure and the circulation. One of the most important gateways to form, there are two important gateways. There was the Tasman Sea Gateway and the Drake Passage opening between South America and the Antarctic Peninsula. So you might ask, how do we know that this happened? Prior to breakup, both South America and the Antarctic Peninsula, if you look at the fossil record, they have the same fossils. You had the same terrestrial fauna present. Okay, so animals, vegetation was able to move readily between the two continents. After 56, 57 million years ago, these faunas began to diversify. So we didn't have a land bridge by that time. We had, there was a seaway between them. We couldn't exchange between the two continents easily. That's known as Simpson's splendid isolation. So with continental separation and the formation of the Tasman Sea Gateway and Drake Passage opening, it led to the formation of a large circulation system known as the Antarctic Circumpolar Current. This is driven by the strong westerly winds. And the key thing about this current is that it moves very fast, both at shallow and deep water levels, so throughout the whole water column. And it prevents warmer waters from the South Atlantic and the Pacific coming further south, travelling further south and reaching Antarctica. So it's been cut off from warmer waters. And it's that process that people argued led to the ice expanding over Antarctica about 34 million years ago. If you look at the Antarctic circumpolar current today, it's actually not one current, it's a whole series of what are called different flows at different levels. But if you look at the amount of water passing through Drake Passage, it flows at a rate of 170 sphere drops, which is 170 million cubic meters per second, which is equivalent to 170 times transport of all the water in the world's rivers combined. So it's an enormous amount of water that's passing through Drake Passage. And some of that water, actually deep water, passes into the Atlantic, and it has a consequent effect on the conditions in the Atlantic and the weather systems associated with that. So it actually has profound implications. The creation of this current has profound implications for the global climate. So that's all very well, but there are problems with this, both of these hypotheses, if you think about it, because with the breakup, at the time of breakup from what was known as Gondwana, Antarctica was not over the South Pole, it was further north, and it moved in that direction between 60 and 40 million years ago. So it wasn't, it was getting a bit more solar radiation than it does at present, is the best way of looking at it. So it's not just about creation of gateways, it's actually about moving the whole continent further south as well. If we look at the CO2 record, what is interesting is that CO2, if you look at the proxy data, CO2 has been low to the same, at similar levels at the time at which the ice was supposed to nucleate, but the climate was a lot warmer at that time. So it can't be just CO2 alone driving that cooling, driving the ice formation. Something else must be going on. And the other thing, if you're going to argue that global CO2 is the main driver for the freezing over of the poles, why didn't the North Pole freeze over at the same time as Antarctica? In fact, the North Pole only froze over around 5 million years ago, some 30 million years later. So it's not all CO2. And yet, I say and yet, there's a rather strong community out there that's still pushing the CO2 message. And there's been numerous papers, especially by Rob DeConto and Dave Pollard, published in Nature, pushing the message that declining CO2 was the key, the principal driver for the glaciation of Antarctica. And they, using their own climate model known as Genesis, suggest the tipping point is around 780 ppm. So they've gained a lot of credibility. They're good speakers. They sell a good message. But that's one climate model. Now, there's a nice study by a young guy called Ed Gasson, who actually spent time at Dave Pollard's lab in Massachusetts, learning how to do climate modelling. And he went away, and what he did was rather interesting. He looked at some of the more widely used climate models that are out there. And these are the climate models that are used by the IPCC, the Intergovernmental Panel on Climate Change, to make future predictions. Okay? Especially the HAD-C model, that's the UK Hadley Centre model. And Genesis. Now, what he did is he put in the same amount of atmospheric CO2, let these climate models run, to predict how much ice would exist for that atmospheric condition on Antarctica. So in Bob and DeConto and De Pollard's model, at 600 ppm CO2, you have a fully glaciated Antarctica. It's covered with ice. On the Haddon Centre model, there's only a few little pockets of ice. Completely different, but using the same boundary conditions. So in other words, there's something in the physics of these models that are actually subtly different. Now, is that because they're actually not describing the physical processes accurately? Or is it because that they're missing some of the interconnected processes, the teleconnections? It's a bit worrying, isn't it, if to have that sort of difference. The thing about looking at these models over geological timescales is it sort of magnifies any small errors or weaknesses in the model that you don't see when you're modelling on the short timescales. So on that basis, you know, if that's your model, of course you're going to sell that as being correct. That's the cause of glaciation there, because I can drop CO2 and I've got lots of ice. If that's your model, you wouldn't argue that. So we're still in a bit of a mystery as to the true cause of the glaciation of Antarctica. What else? Well, if we look at the CO2 proxy data that we base our reconstructions on, look at the error bars on some of these data. They're massive. Okay, we're getting a best fit 9 through those, but the uncertainties on those, well, we're not showing the errors on the best fit. The further back in time you go, the uncertainties get larger and larger. So we need to improve the quality of our data to really be confident about what we're modelling. And the other thing is that if we go back to these model predictions, okay, that's a prediction. Let's go and test that and look for the geological evidence. If we're saying 600 ppm existed at 30 million years ago, let's find some rocks that are 30 million years old that show us there was ice everywhere. That's what we need to do to test these models, to validate these models. So that's something I've been working on recently, and I've been using some core samples that have been drilled by the Ocean Drilling Programme. The Ocean Drilling Programme has been through a number of different name changes. It's now called, the International Ocean Discovery Programme. But basically what it is a collective of countries that have got together, pulled their money to fund a ship to go around the world to drill into the ocean floor to recover cores that scientists can then do some research on. So back in 1987, the ODP drilled a core just to the south of South Orkney Island, which is just off the northern tip of the Antarctic Peninsula. Now, what is interesting about this core is that, unlike the other cores around Antarctica, it has the largest age range going back into the oldest rocks that span what is known as this Eocene-Oligocene transition. So this is the critical time when people think the ice record shows, the geological data shows ice expanded on Antarctica, but we've got very few areas that provide rock samples for looking at before that, the condition of Antarctica before that. So I've looked at this borehole to see what we can find. And the location of this borehole is actually quite interesting because it's at a location that today falls within what is known as Iceberg Alley. There's a very strong coastal current here that mixes with what is known as the Weddell Sea Gyre. So any icebergs that are breaking up from the coast here get caught up in this current and get transported north into the Scotia Sea. This would have been the situation 30, 40 million years ago. It wouldn't have been very different because the geography was practically the same. We know that there's a Weddell Sea here at that time. So if there was any early ice on Antarctica and icebergs were forming, they would travel along this iceberg alley, they start melting, and they would deposit any sediment that they're carrying as they're melting. As the base melts, the sand grains will drop out onto the seabed. So we'd have a record of that early ice. So this is a good location. If ice existed on Antarctica well before people think it froze over, this is one place where you might find that evidence. So I've looked at the number of cores that go through the basically sand-rich cores. Now the obvious thing you might say is, well, isn't that sand just come from South Orkney, erosion, the rivers draining South Orkney, or further over here would be the Antarctic Peninsula. Yeah, so 30, 40 million years ago, where are we? This little block here, known as the South Orkney microcontinent, was actually appended to the tip of the Antarctic Peninsula, and then it got pushed over here by what is known as a rifting event. So maybe the sand has just come from local sources, either from here or from here, rather than icebergs. That's one thing we can test by what is known as provenance analysis. The samples span, as I mentioned, this critical period just before the ice. We know the ice sheets formed. We have that paper, a nice study published in Science by Gagliotti, that shows quite unambiguous evidence that the ice sheets, there was permanent ice by 33 million years ago. But what about before that? Does that mean there was no ice? Does it mean there's a little bit of ice? So the sand grains that we've looked at from these cores, I've looked at over 270,000 grains. That's what I do in my spare time. The interesting thing about these quartz grains is they have a classic shape. They have mechanical fractures that you can only get by ice action, ice breaking them up. So these are typical grains that you would expect from an iceberg that's dropping its load. So this is our first suggestion that there was ice present. Now, could it be there from local sources? So I'm actually a geochronologist. So one of the things that I like to do is play around with the zircons that Philip mentioned earlier. Using a laser ablation ICP-MS, I drill little holes in these zircons so I can measure the isotopic ratios of uranium and lead. Because that will tell me, uranium being the parent, the lead being the daughter, that will tell me the formation age of that zircon. Now you can use dating of individual grains in a sand to build up a histogram or fingerprint of the age distribution in that sand that you can then compare with known fingerprints, age distributions from areas that you think the sand might have come from. So we can test if they've come from a local source, because we know the ages of the rocks on the South Orkney, we know the ages of the rocks on the Antarctic Peninsula, so we have a distinct age histogram, probability plot, or more accurately kernel density estimated plot, that we can compare against. So if we look at local sources, these green down here is the age spectrum from the sand grains from the ODP sites, and these are the very sort of much simpler age structure from the rocks that you find along the Antarctic Peninsula and on the South Orkney. They should be the same because that was once joined to there. But you can see they're different, aren't they? We don't have this peak, we don't have that present on there. They're not the same. That doesn't mean there wasn't some input of local material, but there's a lot of other material coming from somewhere else. So expanding comparisons to rocks that we know that are outcropping in this part of East Antarctica, known as dry moorland, coastland, around the edge of the Filchner Shelf onto the southern Antarctic Peninsula, we get these just, a whole selection of different age spectra. And I've included the tip of South America, of course, because that was much closer 40 million years ago, so it could have possibly come from South America. Where are we? So that's what you see here is just a comparison from all these different areas in terms of the age structures with the ODP samples. And it's very difficult to make a visual, you can make a visual comparison, but it's not very robust, so we apply a statistical method to compare the samples based on what is known as the Kolmogorov-Smirnov statistic. And it just pops a map of sample similarity. So green are the ODP samples, local sources, South Orkney, North Graham Land, which is the Antarctic Peninsula. They're far away in space, they're not the same. South America, very different. Similarity, they all cluster around here, are these areas. So what we've got is evidence that sand grains have come from here and they've ended up being deposited there. The only way in which they can get there is by transport from icebergs. There's no other way. So we have clear evidence for ice. We have the ice-shattered grains, we have the provenance of the zircons. The ice existed along this region, which is quite a large area, well before that main expansion of ice that people see around 33 million years ago. So it's this type of evidence that we can then put back into those climate models to see which ones are correct and which ones are not. So I'm not giving you a complete answer, but it's a demonstration of the sort of things that we need. We need more information of this type to validate these climate models and to know which ones are really realistic. So we just published that with colleagues on the British Antarctic Survey this year. We also need to improve the tectonic models because this formation of the Antarctic circumpolar current, our tectonic models are very rudimentary in terms of people just draw little blobs that they think existed at the time of separation. And they draw little blobs because we have along here what is known as the North Scotia Ridge. These are microcontinental blocks that have originally were located between, originally part of South America or the Antarctic Peninsula, and during that separation process they get pushed up over here by a new formation of new oceanic crust. Most of these continental blocks are below sea level. The only exposed parts are South Georgia, which you've probably heard of, and a few little pinnacles of rocks sticking up called the shag rocks. Now, we need to understand when these little blocks moved over to create the North Scotia Ridge. We need to understand if they were ever subaerial during their translation to their present locations, because that would have impacted on the ocean currents that formed the early Antarctic circumpolar current. If we've got that information, we can then improve climate models, because the climate models not only model what's going on in the atmosphere, they model the ocean flows and the ocean temperatures as well. So I thought I'd have a go at going to sample these rocks, but no one was prepared to take me on a boat to go and sample there, because it's just too dangerous. In fact, the British Antarctic Survey ship won't even go within 50 kilometres of them. They were sampled actually back in 1977 by helicopter, by someone from one of the Royal Navy ships, but the rocks were lost. They didn't do a very good sampling. But that's the only exposed part of a continental block that covers 11,500 square kilometres, and we know nothing about the geology of this region. And so, given that I can't go there, I persuaded the British Antarctic Survey to go and send a ship and dredge some rocks from here so we can sort of scrape some rocks off these submerged blocks to see if we can learn about their history from the rock samples. So the James Ross Clark went there just before Christmas, and using a very primitive apparatus, basically a chain link net, just scrape some rock off the seabed. I was unable to go because I was moving laboratories, or supposed to be moving laboratories at that time. My colleague Charlie Bristow kindly stepped in and regretted it. He regretted it because the cruise, rather than lasting 1 month, went on for about 6 weeks, and it crossed over through Christmas for various logistic reasons that the British Antarctic Survey came up with, which I won't go into. So that's research in progress. So we're making steps to better understand the geology so we can better understand the evolution of these ocean currents. Now, why are they important? Now, you might argue that these currents are not important. You know, we shouldn't have to worry about how the North Scotia Ridge developed. We know the Antarctic circumpolar current formed. Isn't that good enough? Well, if you look at these, the interaction of the ACC, as it's known, you can see that it actually produces currents right into the northern hemisphere of the Atlantic. It reaches into the Indian Oceans, it reaches into the Pacific. You know, it has big implications for the it transports cool waters into these regions. It has a cooling effect. That affects climate in the northern hemisphere. The character of these flows is defined, believe it or not, by the arrangement of these tectonic blocks in the North Scotia Ridge. So if you change that pattern, it will modify these circulation systems. So it's critical we need to understand it. Now, the latest research that has just come out, again using a climate model of a sort, but it's actually very interesting because it sort of supports my line of thinking, so that's rather biased, but here we go. It's published in Nature Geoscience 2 weeks ago, 3 weeks ago, very recently. Anyway, what they did is they modelled the effects of Drake Passage opening in terms of how it affected the northern hemisphere, so that it looks beyond the Antarctic region. And the interesting thing is that the opening of this passageway and transmission of some of these currents led to temperature changes. Increased warming in the northern hemisphere and cooling in the southern hemisphere. But this warming drove increased precipitation in the northern hemisphere. If you increase precipitation, you increase temperatures, you increase weathering. So if you're increasing weathering, you're increasing CO2 drawdown. So this is one of those unexpected teleconnections that I was alluding to right at the beginning. You know, it's a complex system. So increased silicate weathering, increased drawdown, that's the link to Antarctic glaciation. So it is CO2, but it is tectonics. It's the opening of the ocean gateway. So it's both of those hypotheses. Rather than name them, it's a bit of both. Of course, this is a model, and I can't stress enough that we do need to ground truth those models with more geological evidence. Okay. And that's where we're heading at the moment. So I'll conclude by just saying that, we said that the decline in CO2 and CO temperatures that allowed the expansion of ice around 33 million years ago was driven by plate tectonics and mountain building, and silicate weathering, and the climate change that affects the CO2. We need more ground truthing, data sets are sparse, and we need to better understand these teleconnections. So it's not just the physics of the individual processes, it's how they connected. The far field, the butterfly effects, effectively. I mean, who would have expected that by opening this little passageway here, you've completely changed the climate regime in the northern hemisphere? But that's the evidence from these models. Okay, I'll end there. Thank you.
Questions for Andy? So how do you know that what you drain off the ocean floor is representative of the rocks you're interested in?
So some of the rocks would have been dropped by icebergs. That is very clear. And they have distinct mechanical features. And we know from the exposed parts, South Georgia and the Shag rocks, approximately what the rock types should be. We know that they've come from the southern tip of South America in that area, so we know the rock's there. So we should be able to make that sort of connection. So we have a reasonable degree of confidence. It's not the same, of course, as knocking it off without.
Yeah.
We know that we get sort of desert sand in this country sometimes. I mean, is there really no possibility that this area of transportation, those grains,
Windblown sand. Yeah, but there could be, but they have a very distinct morphology, so you can recognise them. Certainly, when you have periods of ice, you do get a lot of dust being produced as well.
Okay, I'd like to thank you all for... Oh,
Question. To compare the distribution of ages, you said you're using Smirnov test.
Yes, on a multi-dimensional scaling plot.
Is there any other test you use?
Well, because you're dealing with a distribution of ages, that's one of the better ones to use.
Have you ever used the Kullback-Lever divergence test?
That's beyond my comfort zone. I mean, the package that we use was put together by a chap who's very familiar with, well, he's partly a statistician, so we have confidence. And that method is also used in other disciplines as well.
Okay, well, thank you all for attending Science Week, and a big round of applause for all our speakers this evening.